So, good morning, everyone. So now in this talk, I'm going to talk about executable formats and how we can modify them to do interesting things like code injection or hooking. So I'm Romain Thomas, I'm security engineer at Quartzlab, which is a French security company. And I'm mainly working on obfuscation, disobfuscation. I'm also working on Android and developing new tools to automate some part of the reverse engineering process. So about executable formats. The format is basically the first layer of information when you analyze a program. It provides some metadata to the operating system, like the entry point or the library that are used by the program. And the operating system uses this metadata to load the program. So there are mainly three kinds of formats. The first one is used on OS X and iOS, and it's the Macro format. The second one is used on Linux, and it's the ELF format. And the last one is the PE format, which is used on Windows. On Android, it's a bit special because Android is based on Linux, so they also use the ELF format. But recently, they add the OAT format, which is a kind of extension of the ELF format. So why it can be interesting to modify formats? So if we look at this diagram, here we have the program that belongs to the user land. And we also have two components, which are the loader and the kernel. And these two components belong to a more privileged area. And actually, when you run the program, the loader will perform relocation associated with the program. It will also load the shared libraries that are used by the program. The kernel will create process, and it will also map section and segment defined in the formats. It will also set permission on this segment and section. So basically, these two components use information from the user land. So for example, if you want to change the permission of a section or of a segment, you can just change the permission in the formats, and the kernel and the loader will set the permission according to the formats. We can also add some dependency to the program, and the loader will load your new dependency. So the main idea is that the two components use information from the user land to do more privileged process. And for example, if you are on a PE file, in the PE file there is a special attribute in the optional header that enable or disable the ASLR. So if you want to run your executable without the ASLR, you can just disable the ASLR using a modification on the format, and the loader and the kernel won't use the ASLR on the program. So how we modify these formats? We develop a library which is Leaf, and behind this project, we aim to provide a single library to deal with the formats. So we actually support ELF, PE, and Mako, and we also aim to provide a user-friendly API to interact with format. So we have a Python API and C++, as well as C API. So basically, the architecture looks like this. So here we have the format, and we have the parser module that takes the format as input and transform this format into an object representation. From this object representation, you have an API to modify the object. So for example, if you want to add a flag or disable some part of the flag, you can just interact with the object representation. Here you can also add some section, or you can modify permission, for example. Then we have the builder module that takes the object representation and transform this object into the raw formats. So here is an example where we take whatever format, so we can take ELF, PE, or Mako, and we just print the entry point. So here is an example of the Python API. Here, we iterate over the section, and we print the virtual address of the section, and we do some process on the content of the section. Here, we'll take a PE file, and we'll just add a new function into the TLS callbacks. Here is another example where we create a new section. We fill the section with an op instruction, and we just add the section to the target. And we reconstruct the final binary. So in the next part, I will introduce some modification on this format, and we'll see how we can do hooking, how we can re-export hidden function, and how we can do code injection with shared libraries. So about PE hooking. In the PE binary, you have a special section, which is the import address table. And basically, when you run the program, this table will contain all the address of the imported function. So, for example, here, if we import this library and if we import this function, once the program will be loaded, this address will contain the address of this imported function. And what we can do to do hooking, we can just relocate this import address table elsewhere in the binary and patch this original table with trampoline function that will jump either into the hooking function or it will jump into the new import address table. So with Leaf, we can do this operation by using the hook function. So here we'll hook this function with this new function. So now when there will be a call to this imported function, it will be redirected to this address. And we specify to the builder that we want to move the import address table elsewhere in the binary. And we also specify that we want to use trampoline function to redirect function. So now when we do this operation, it will relocate the import directory as well as the import address table in a new section. So here we create a new section that will contain the new import address table. So here is a new section that has been created. And the original import address table is now contains some trampoline function. So here is the trampoline function. And we can have two kinds of trampoline function. The first one is if we don't want to hook the function. So if we don't want to, we just jump to the original import. And if we want to hook the function, we now have a jump into the hooking function. So actually, this method only works if there is call instruction on the import address table. I mean, if there is some load effective address on the import address table, there will be some load address of the trampoline function, so there will be a crash. So this is the main limitation of this method. So regarding the ELF file, we can use the PLT-GOT mechanism to do hooking. So basically, if your program somehow calls let's say, the memCompare function, it will first jump into the PLT section that contains a trampoline, but actually this trampoline is generated by the compiler. And from the PLT section, it will jump into the GOT section. And actually, the GOT section contains either the value to the memCompare function from the libc, for example, or it will contain the address of the next instruction into the PLT that will do the resolution of the memCompare. So what we can do to do hooking, we can just replace this value with the hooking address. So the problem is how we can resolve this address. Because if you are able to resolve this address, you can just patch this address in the program and you can modify this value. So actually, in the ELF format, you have a special relocation associated with this address. And this kind of relocation is a jump slot relocation. So what you can do to do the hooking, you can just iterate over the row location that are associated with the PLT got section, check for the interesting address, and just patch this address into the binary. So using Leaf, you can use the patch PLT got method. So you specify the symbol, and you specify the address of the hooking function. And you reconstruct the program. And now the flow of the program is the follow. So first we jump into the PLT, then we jump into the GOT, but we patch this value, so now it will jump into the hooking function. So now I will move to another modification that is the exportation of function. So basically, you can have a program, and the program will take some input from, for example, argv, and this input will then go through internal function, a lot of internal function or a very complicated condition. Then it will go to the check function, that is the function that you are interested in, so you want to analyze this function. And from this function, it will return some value again into internal function. And it will go then into the output that the user can handle. So if we take what we want to do, basically, we just want to interact with the check function. For example, to fuzzing or to instrument the function. We don't want to go through all the internal function, or we don't want to resolve the very complicated condition that enable to access to this function. So let's move to an example. So let's say that I have this code. So here we have a very complicated condition that is very difficult to resolve. And it takes the argv1 as argument. So if I compile this code without debug information in the release mode with optimization and so on, I will get this CFG. So here I have the condition, and here I have the call to the fuzzme function that is not associated with the symbols, it's just a call to an address. That is normal. And if I look at the symbols associated with this program, I can see that all the symbols are imports. I mean, the value is set to 0, which means that we are importing symbol. We don't export symbols. And what we can do, we can add a new symbol associated with the function. So actually, we can do add exported function. So now I will associate this address with this name of function. And now I can see that my program has a symbol associated with my address. And actually, this symbol is exported. So now I have a new symbol that is exported from the format, and I can use them by using, for example, dlsim or dlopen. And actually, it looks like quite simple to do, but moving or extending the symbol table of an ELF format is not very easy. I mean, if you already try, it's very, very complicated. And now I can directly interact with the fuzzme function by using dlopen and dlsim on the two-fuzz function. I forgot to say, but we assume that the original program is position independent, so that we can load as a library. So yeah, we assume that the original program is PIE. So now I will move to the last modification, which is code injection. So actually, there is different technique to do code injection. You can use environment variable. You can also use operating system API like ptrace or write process memory. And you can also use custom kernel driver, or you can use formats. And depending on the scenario, some methods are suitable or not. I mean, if you are on a desktop environment, you have the privilege to do ptrace because you can be root easily. But if you are on a smartphone, for example, you don't usually have a jailbroken device or a rooted device. So you can't use ptrace for it. But if we go back to this diagram. Here, the loader, when he loads the program, he iterates over all the dependency and all the library. And what the loader do, it will map the library into the process memory, and then it will call a special function, which is a constructor. A constructor is a function that is called each time the library is loaded. And what we can do, we can just add a new dependency into the program, let's say libexample.aso. And when the loader will load the program, it will load the new dependency, and it will call the constructor. This is the purpose of the loader, to load library within the process memory. So this is the loader that will do the injection. We just add a new dependency to the program, as we will do, for example, for the libc, and the loader will just load the library into the memory space of the program. So here is an example of such library. So here we define a function that will do a printf with run payload, and we associate with a special attribute that defines this function as a constructor. So by using this attribute constructor, this function will be set as a library constructor. Then I will compile the program as a library. So here is for Linux library, and here is for OS X library. And now I will use leaf, and I will add a new dependency to the SSH program that is libexample. Then I will reconstruct the binary. I will do the same for Mako. So I took the ls program, I add the new library, and I reconstruct the program. So here we'll add a new load command into the Mako format. Actually, it's not implemented yet for PE formats. And now, if I run the ls program here, so here is the normal execution, and if I run the new program with the new dependency, I can see that first I have the run payload at the beginning. So here is the call to the constructor. And if I look at the dependency of the modification of ls, I can see that I have a new lcdilib command. So here is a new dependency that has been added by leaf. And in the same way for ELF file, I can see that in the SSH, the new SSH program, I have the new libexample.aso dependency, and now if I run SSH, I have the run payload that is print before the normal execution. And I'm not using root, or I'm just a normal user, and the loader do the injection. So one application of this technique is with Frida. So Frida is a framework that do dynamic instrumentation. And there is different mode of operation. And in the default mode of operation, Frida somehow need to inject code into the target process. And the default mode of injection is with ptrace. So Frida is doing ptrace on the process to inject Frida agent. There is also another kind of mode of operation that is libgadget. And basically, libgadget is a standalone library of Frida. So libgadget contains all the logic of Frida, but the user is responsible to inject this library within the process. So here we took the Telegram application, and we inject the libgadget into the native library. So here we just added the libgadget.aso. We also added the libgadget.config.so that is used by libgadget to find, for example, the Frida script that has to be executed by Frida. So here is the configuration file of libgadget, and here is basically the main logic of Frida. And what we did, here is the original dependency of libtmessage from Telegram. So here we have the GNI library, we'll have the liblog library that is used for logging purpose, we'll have the libc and so on. And by doing the same modification as described before, we add libgadget.aso. And now we repackage the APK, we resign, and we install the APK as a normal user. And just by running the APK, the loader will load all this library, especially the libgadget that contains also a constructor. And this constructor will look for the Frida script and load the Frida script and do the instrumentation of the application. So here is a configuration file of libgadget. So here is the path to the Frida script. So here is myscript.js in data local TMP. And what I do in this script, I just resolve the log class to print that I'm in the process of the application, and I will enumerate all the library that are loaded within the process. So let's move to the demonstration. So here, I just run the Telegram application. I'm not on a rooted device. I mean, you can try by yourself, but it's not rooted. So here is so the application is run, okay. And now, so I will just do logcat with the special tag Frida leaf with the verbose mode. And okay, so now so I can see here that libgadget is in the memory space of the process as well as libtmsage. Here we have all the libraries that are loaded by the loader, and I am in the process of the program, so I can do what I want in the process memory of the program without being root. And you can do your instrumentation, or you can use your Frida script as you did with the standard mode of operation. So actually, this kind of modification is not new. I mean, it has already been described in FRAC 61 in 2003. And there is also some libraries that is doing some injection of load command in macro formats. But actually, the way it's implemented in Leaf is different. I mean, we are not using some hack like padding or removing entry or replacing existing one. Instead, we keep a very consistent state of the format. And for example, when we add some new load command in the macro format, we rebuild the export try, we patch the rebase of code, and so on. So we really keep a very consistent state of the format. Same for the ELF format. When we add symbols and so on, we keep the consistent states of the symbol H table and so on. And it's enabled to do very strong modification. In the latest test, we were enabled to add a lot of load command in the macro format. We can add unlimited number of dependency in the ELF format, which is not very trivial. And yeah. So we released Leaf version 0.9 a few days ago. And actually, it also comes with new formats related to Android. But actually, it's only read-only on this format. But we plan to add some API to do modification on this format. And actually, if you look at the talk last year at Black Hat about Samsung Wallet, one way to attack the wallet was to modify OIT format, because actually OIT format contains native code, and it's located in the data partition of Android. And the data partition is not limited by DM Verity. So you can add some code in the OIT that will be loaded without DM Verity. Also, last year, there were talk about safety net, and one way to bypass safety net is by modifying the OIT format, which is actually an ELF format. So if you look at the OIT, it's an ELF, a special ELF, but it's an ELF. So you can do the same tricks as I did with adding new dependency. So actually, the modification of the macro format is not available in the public version of Leaf because we have to do some tests, but it will enable to add unlimited number of load commands in the macro format. It will also enable to add libraries as well as changing the signature, for example. So the project is on GitHub, so you can compile and try by yourself. We also have some tutorial on the official website. And thank you for your attention, and if you have any questions.
So let's have some quick questions to stay in schedule.
No questions? Okay, then thank the speaker.
Thank you.
And let's continue.